You know, when you look at a really high-performance game engine, you're not just looking at a list of cool features. You're actually seeing a philosophy. Today, we're going to pull apart the blueprint for V-Engine to understand its core belief, which is that top-tier performance doesn't just happen by accident. Nope, it's a deliberate, disciplined architectural choice. Let's see how they pull it off.
All right, so here's our roadmap. First, we'll get into the fundamental problem V-Engine was really designed to solve. Then, we'll walk through the 5 foundational principles that guide its entire design. After that, we'll see how it handles data and logic. And finally, we'll check out the hard-won architectural decisions that prove this whole philosophy actually works in practice. So, what is this core problem we're talking about? Well, it really boils down to a fundamental conflict. See, the way a lot of us learn to program, with traditional object-oriented principles, is often actively fighting against the way modern computer hardware, modern CPUs, are actually designed to work. And here's that conflict in a nutshell. Traditional OOP, it tends to scatter individual objects all over your computer's memory. It's just a mess. But modern CPUs, they are absolute beasts, built to grab huge continuous blocks of data and just tear through them in parallel. So when your code hands the CPU a scattered mess instead of a nice, neat line, your performance just tanks.
This exact bottleneck has a name. It's called a CPU cache miss. And you can think of it like a performance tax. Every time the CPU needs a piece of data that isn't right there on its desk, in its super fast local cache, it has to stop what it's doing and go all the way to slow main memory to get it. That trip costs over 100 clock cycles, which is an eternity in CPU time. It's the performance killer V-Engine is specifically designed to eliminate.
So how does V-Engine solve this? Well, it's not with one single magic trick. It's with a disciplined manifesto. So let's dive into the 5 foundational principles that guide every single architectural decision in this engine, and the price that they have to pay for this level of discipline. All right, here they are, the 5 pillars. First, a super rigorous spec-first development process. Second, a deep focus on data-oriented design. Third, a pure entity component system architecture. Fourth, a unified system lifecycle. And finally, externalized configuration to keep everything flexible. We're going to break each of these down. This first principle, spec first, is incredibly rigorous. Every single feature starts out as a formal specification document. Then, from that document, the tests are written. And only then is the actual engine code written with one single goal: make those tests pass. It's a huge investment up front for sure, but that's the price you pay for absolute predictability. And this isn't just some vague guideline, it's a serious commitment. The engine is validated by over 5,900 test assertions, and every single one of them traces directly back to a spec document. That is how you build a system that's truly robust. Now for principle number 2, which gets right to the heart of that performance problem we talked about, data-oriented design. This is all about completely rethinking how we organize memory to work with the hardware instead of fighting against it. This shows the difference perfectly. On the left, OOP scatters whole objects all over memory. But look at the right. Data-oriented design groups similar data together. So all the positions are in one continuous block and all the velocities are in another. This clean, organized layout is exactly what a modern CPU is built for. So why does this matter so much? Because a CPU always grabs data in 64-byte chunks, and these are called cache lines. By keeping all that similar data packed together, every single byte the CPU fetches is useful. There's zero waste, and zero waste means maximum speed. The magic behind this is a really clever data structure called a sparse set, which V-Engine gets from the popular NTT library. It's the key that allows the engine to keep all these components perfectly packed in memory for the CPU, while still letting us access any single component pretty much instantly. It's the best of both worlds. Okay, so having our data perfectly organized is great, but that raises a question: where does all the logic go? And that brings us right to our third principle: implementing data-oriented design with a pure entity component system, or ECS architecture. So, let's break down ECS. First up, the E stands for entity, and you have to understand, an entity is, well, it's basically nothing. It's just an ID, a unique 32-bit number. It has no data, no logic, it's just a simple tag that represents a thing in the world. Next up is C for components. This is where all that beautiful, organized data lives. A component is a pure data structure, just a plain old struct. It's got your state, like position or velocity, but, and this is an absolute hard rule,
It has 0 methods. All logic is completely banned from components.
So where did all that logic go? It lives here, in the S, the systems. 100% of the behavior is in the systems. For example, a physics system will just ask the engine for all entities that have both a position and a rigid body component, and then it will just blaze through those perfectly contiguous arrays of data to do its calculations.
And these systems, more than 30 of them, are all orchestrated in a really strict deterministic order every single frame. The engine guarantees that first input is processed, then physics and AI are updated, and then rendering happens. This ensures that all the behavior is perfectly consistent and repeatable. That's absolutely critical for debugging, and it enables a deterministic input harness for perfect game replays.
So, we've covered the philosophy. Now, let's look at the proof. We're going to examine some of V-Engine's key architectural decisions, which were all formally documented, to see how these principles translate into real-world, measurable performance.
These decisions are captured in what are called architectural decision records, or ADRs. The very first one, ADR-001, documents the choice to use a thread-based job system instead of something like fibers. And why? Well, it's a super pragmatic trade-off. Threads are just way easier to debug and profile with standard tools, and that's a massive win for productivity.
And the results? They really speak for themselves. The team benchmarked their system against the job system from the Decima engine, which powers Horizon Zero Dawn. The target was to process 1,000 jobs in 6.5 milliseconds. V-Engine's system does it in 4.5 milliseconds. That is a significant performance win.
Here's another critical one, ADR-009. It established a strict zero allocation policy. Now, what that means is that in the most performance-critical code paths, the hot path, like submitting a job or sending an event, the engine is absolutely forbidden from allocating any new memory from the heap.
And a quote from the documentation really explains why this is so important. Basically, standard C++ memory allocators can be really unpredictable, and that causes performance spikes. So by using pre-allocated pools instead, V-Engine achieves totally deterministic memory behavior. It guarantees a frame won't suddenly stutter just because the system decided it needed to allocate some memory.
This discipline is just everywhere. Take ADR-008, the engine is Vulkan only. That's a choice that sacrifices broad compatibility, but it gets them direct, low-overhead access to modern GPUs. For stability, there's that deterministic input harness we mentioned, and to kill an entire class of weird timing bugs, it exclusively uses a steady clock that can't be messed up by system time changes. Each one of these is a hard choice, a trade-off made for performance.
And this brings us right back to where we started. V-Engine proves that elite performance can be achieved by design. It's not luck. But this level of discipline comes at a price. It's the price of rigor, of strict rules, and of rejecting convenient but inefficient patterns. And it forces us to ask a really important question. If performance is a feature, what is its architectural price?